Hello and welcome to our preliminary design review. We're the LU Rocketeers. I'm Sam, the team lead, and this is Andrew, my vice team lead. Our majority member share in this room is based at Lancaster University, with 2 remote members also part of the team, Artem from the University of Warwick and Luke from City Uni in London. So I'll let everybody introduce themselves one by one.
Hi, my name is Anthony Royster and I am a second year mechatronics engineer. I am the lead structural and PCB team and I'm handing over to Jasleen.
Hi, I'm Jasleen Kaur. I'm doing mechatronics engineering. I'm third year student and I'm passing out to Shad.
Hello, my name is Shadi. I'm part of the structural team and I'm second year student.
Hello, my name is Kai Stewart. I'm a first year physics student and I'll be part of the modelling team.
We've divided our team of 13 into 3 groups. I lead the modelling and simulation team, Andrew leads the guidance team, and Anthony, who introduced himself, leads the structural team. So in this presentation, we'll be covering 6 main topics. So we've listed our objectives here as part of our mural board, which Andrew will present later. So we're going to reach an apogee that's the target. We're going to demonstrate aerodynamic control by using canards. We're going to manufacture a reusable rocket by having a Aerotech casing, which will reload our motor. And we're going to try and collect as much flight data as possible, including a little gimmick to set us apart from the other teams, which we're going to use Q-learning.
Thank you very much, Sam. So this is FreeCamp, our online project management tool. FreeCamp allows us to assess all of the tasks and assign them to each member. This is our mural planning board, so it's basically a big whiteboard where everyone can put their ideas onto the main board, and this is how we collect all of our information so everyone can see it. Long-term management, so this is our Gantt chart, so this is how we are managing everything in the long term, as I mentioned. So it's split up into our 5 key reviews and deadlines. The important part, money. So these are the main parts of our budget. So PCB, you can read all of this. And we also have the overall cost estimate of £460.
Moving on, I'd like to go into deeper detail on my team's progress with simulations. On the right here is a compiled list of every requirement from the technical specification. In our simulations, we've tried to adhere to such constraints to create the most realistic model of our future flight in order to advance our decision towards which motor to choose. For these simulations, we've been using OpenRocket. In the program, we've included extra components such as the rail buttons, tube couplings and bulkheads in accordance with each section of the specification. In our first round of simulations, we attempted to learn the software and soon discovered the difficulty of designing the rocket to meet all of the constraints. Here are some examples from Avantika and James, and where we tried to initially decide what were the most important components to control. As we reached the second round last week, I instructed a more refined set of designs as shown here, which have supporting simulation data sets. We have tried different fin shapes, body tube lengths and nose cone designs. With research support from the structural team, we were able to produce 4 models in total that meet the majority of the specification standards. The data of these 3 in particular show a common trend. The best performing motors appear to be the Aerotech models G64 and G76. They both regularly achieve the sufficient velocity off-rod, which is 20 meters per second, so here, here, and here, and reach apogees at least 100 meters beyond their Cesaroni motor equivalents. To decide between these motors, I set up a custom 5th comparison simulation. The G76 appears to be the best performing in terms of consistency with the other simulations. It supports a delay range between 7 seconds and 10 seconds and doesn't deviate far from the target altitude. With the addition of the canards at the front, we have optimal control for keeping the rocket to the exact altitude that we need. The resulting motor plots for altitude make use of a 10-second delay, which places the ejection charge within half a second of reaching apogee at the peak here. This means the recovery device will deploy when the rocket is at its slowest speed, which means it is at its safest point, and then it will gradually descend over the next 2 minutes. As for the stability of the rocket, it stays fairly consistent all the way until apogee, which is here, and from the motor burnout until that point, it remains at about 2.55 calorimeters, which basically means that it's within 2.55 diameters of distance between the center of mass and centers of pressure during flight. Now this does fail the technical specification, but only by a margin of 0.05, which means that it can be easily corrected by changing the fin height in the program. Future simulations will improve on our progress towards the beginning of the critical design review, and we intend to utilise 2 additional methods. To verify the data gained from OpenRocket, we're going to use RAS Aero 2, which provides a more refined aerodynamic analysis. And to set ourselves apart from the other teams, we'll be attempting to use the expertise of Mars and his PhD theory to run Q-learning simulations on the rocket and find optimal solutions to our design constraints.
So in our design, we've made sure that our rocket is unique and it has elements that allow us to be different from the competition. So in our rocket, we have gone the main thing with a canard design for active aerodynamics. This allows us to change the rocket's trajectory. Stuff we've made sure to emphasize, so it meets technical regulations as well, is the fin height. So the fin height in this design has been iterated to be optimal. So if we increase the height of the fin, that gives us more stability. However, we are limited that with the technical specification. If we decrease the fin height, that moves the center of pressure towards the left and towards the center of mass. That will give us a higher apogee. However, it will make the rocket less stable. So we've gone with an optimal design there, and that will be further iterated when we move into the second design phase. We've got mass components here to offset the center of mass to make sure that it is most stable as possible as well. Last thing, for the length to diameter ratio of this specific design, it's got 479 millimeters long and 41 millimeters in diameter, so it meets that specification as well. So, as we mentioned before, the motor we've gone with is the G76. This provided the most consistent performance across all of our simulations. So, the way the motor works is we have burning solid fuel. Once it reaches its total burn, which is about 2 seconds, it will start a preliminary charge. The fuse will then light up, and once it reaches the end, a charge will burst. That charge will separate the rocket. So when that charge bursts, that change in pressure will force the rocket apart. In the lower part, this picture here is at the top, and we have the 2 sections of the rocket tethered to the same parachute. So the shock cords will help the parachute to unravel and deploy, and our rocket will come down safely. So there will be one 116 Kevlar shock cords, each 2 meters long, to support the splitting of the rocket. So we have accounted those in the budget as well. Can I have the next one, please? Thank you. So to integrate the customer's payload, we have gone with this is a simple 2D sketch of our model. We've got the main stage with the bulkhead and then the flight computer, which will be here just above the canards, and the PCB will be there as well. The customer's payload will be below the canards, as there will be a camera hole as a part needs to be exposed. We think it's for a camera, but the exposed part will be on here as well, just not accounted for this specific model, which is given to us from OpenRocket themselves.
So hello. So in terms of data collection, we will be collecting 3 types of data. So for positional data, we will be using the gyroscope and accelerometer. For the second type of data, we have the option between the altimeter or the barometer. And the third type of data that we're going to measure is temperature, using a temperature sensor. For the next steps, preparation for the critical design review. So we are going to be doing a final element analysis in SolidWorks, and to meet regulations, to see if the components handle the stress. Because we will be implementing Q-learning, we need to find a processor and PCB that would be appropriate. And we will be assessing fluid dynamics of canards and structural elements to find the right torque, to find the torque required, and to buy the right servo.
Right, so for the final part, I've compiled a project risk document. So I've put this into 4 sections: management, design, manufacturing, and the actual launch. So for management risks, this is basically if me and Andrew don't do our job, then we've got a risk in terms of that. We've also got risks in terms of the design, because we need to keep the team on track and make sure we adhere to the technical specification. Then manufacturing and rocket handling are physical hazard risks to health. So those are the 4 sections that we've considered in terms of risk. Thank you, and bye.